All right, good morning, everyone. Welcome back to Math 161. So this is week two, day two. Week two, day two, our fourth meeting together. Keep an eye on the TCC schedule and website if you have any Friday classes. This snowstorm could end up canceling Friday classes. I certainly don't know. I'm not an admin. I think by the time we come back to class on Tuesday, everything will be normal, so hopefully no issues there. But do be warned that if for some reason TCC closes on Tuesday, we don't want to fall behind. I do have videos available that I can post on YouTube for our class and in our Canvas listing so that you would just be able to watch that on your own time. But again, I don't think that's going to be an issue, at least this coming week. So we're going to pick up right where we left off in section 1.3, models and applications, which means word problems. We did one example of a word problem. And then we introduced what a linear cost model looks like. It doesn't have to be just a cost model. It can be a linear, lots of different things. And I'm not even going to name those 50, 60, a million different things because it would take forever. But we said a linear cost model is just saying that a total is equal to a variable amount plus a fixed amount, where a variable amount changes and a fixed amount doesn't change. Kind of like your electric bill, which changes every month, and your rent, which doesn't change every month. Yes, it might change after 12 months, rent might go up, but you get the point. So variable amount tends to have a variable paired with it, so something like 3x, 5x, 0.05x. A fixed amount is just going to be a number because it doesn't change. And we're going to go straight into example 2 with that being said, and we're going to talk about old school cell phone plans, where you're actually paying per text and paying monthly fees and stuff like that. And yes, these cell phone plans do still exist, but most people just have unlimited text messages, unlimited minutes, whatever. So you're choosing between two old school cell phone plans. Plan A, which has a $20 monthly fee and costs 5 cents per text. Then Plan B, which has a $5 monthly fee and costs 10 cents per text. And how many texts does your plan choice not matter? Okay, so remember the different things we want to do. We want to go through and identify the knowns and unknowns. So give things numbers, give them variables. Write an equation using our words. And this is after having read the problem several times. I forgot to say that first. Read the problem several times. Label knowns and unknowns. Write an equation using words. Stuff the knowns and unknowns into the equation, then solve the equation. So you're choosing between two plans, Plan A and Plan B. Plan A has got two different dollar amount associations, $20 monthly fee and a per text cost of 5 cents per text. So one of those sounds fixed and one of those sounds variable. One of them depends on how much you do. One of them doesn't matter, no matter whether you send, whether you talk 5 minutes or 100 minutes, no matter whether you send 5 texts or 50 texts or 5,000 texts. And then Plan B has the same two types of values, but different values. And they say at how many texts does your plan choice not matter? So just reminding us here that a fixed cost is something like a flat fee and a variable cost changes based on the quantity. And this tends to be labeled as a per something. So like a cost per item, $1 per M&M or piece of candy, maybe a cost per text message. Ooh, hint, wink, nudge. Whereas a fixed cost is just something that doesn't change, something like a fee. So we can see that Plan A has a fixed cost of $20 and a variable cost, I'm just going to squeeze this in here, of 5 cents per text. Whereas Plan B has a $5 fixed cost and a 10-cent variable cost. So Plan A, if you don't even touch that phone for a month, you're going to pay $20 no matter what. Plan B, you're only going to pay $5. So if you don't text, if this is just an emergency phone that sits in your glove compartment, Plan B sounds better because you're only going to pay $5 versus $20. But if this is your everyday phone and you text 10,000 times a month, I bet you that 5 cents per text starts to make a big difference ultimately. And maybe the $20 flat fee is actually worth paying to get the lower variable cost. All right, so Plan A. And I have these things, some of this stuff already typed up. I don't want to share that yet. I'll type it. It's typed lower, but I'll just go ahead and type it. So the knowns and unknowns. For plan A, we know our fixed cost is $20 and our variable cost is 0.05, which means 5 cents per text. For plan B, our fixed cost is $5, right? Yes, $5. Whereas our variable cost is 10 cents. I'm probably just going to go ahead and type everything up. It doesn't take that long. So those are our knowns and our unknowns. We read the problem several times. We labeled our knowns and unknowns. Next, we want to come up with our equation. Well, actually, it's kind of like 3 equations, because there's going to be an equation for plan A. There's going to be an equation for plan B. And then there's going to be an equation where we do something with plan A and plan B. So plan A's cost, total cost for A, would be equal to. Well, we take the variable cost and we add the fixed cost. Now, if you just do this, the variable cost 5 cents, the fixed cost 20. If you do this, this is wrong, this is wrong, this is wrong, 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 any wrong, any wrong. Oh, Mr. Beckner, you have the variable cost of 5 cents per, you have the fixed cost of $20 per. Why is this wrong? Because a variable cost has its namesake in it, a variable. So it's 0.05x plus 20. For plan B's cost, its total cost for B would be equal to, and I'm kind of over labeling things, it would be its variable cost of 10 cents per, so times the variable, plus its fixed cost, which was $5. And then you might want to say somewhere where X is the number of texts sent in a month. If you're doing this on homework and tests, you have to label everything so supremely? Not necessarily. Is it good practice? Absolutely. Now, what's the goal here? They say, how many texts does your plan choice not matter? Notice that I didn't just read everything 3 or 4 times all together. I dissected this thing. I took it apart. And how many texts does your plan choice not matter? In other words, when are they the same? How many texts do you have to send where plan A's cost ends up being the exact same as plan B's cost? Well, to figure that out, we need to set plan A equal to plan B. Well, plan A's cost is this thing. Plan B's cost is that thing. So we're just going to set those 2 things equal to each other. So we go 0.05x plus 20 is equal to 0.10x plus 5. Mr. Beckner, you don't need to write this 0 right here. You don't need to write that 0 after the 1. Sure you don't. You could just write 0.1x. That is absolutely true. I don't have a problem if you just write 0.1x. So Mr. Beckner, then why did you write that extra 0? Because you normally don't do that. Because we're talking dollars and cents, and it's just kind of a friendly reminder. But again, technically that's what we call a trailing 0, and you don't need it. You can write it, you can skip it, you can write it, you can skip it, nobody cares. It will not affect the answer in any way, shape, or form. I like it this way because we're talking dollars and cents. All right, so this is not a tough equation to solve. 1, 2, 3, 4 pieces. But uh-oh, we got decimals. Can't I just use a calculator, Mr. Beckner? Nope. You gotta know how to handle your decimals. And we said, sure, you can move the 5 and the 0.05 or whatever and divide by decimals. And if you know those techniques, that's fine. But I gave you a better trick. It's to identify the LCD, which for decimals says to go through and find the most decimal places and give your LCD a power of 10 with that many zeros. So if I saw 3 decimal places at most, I'd have an LCD of 1,000. There's 1, 2 decimals here. There's no decimals here. There's 1, 2 decimals here and no decimals here. So the most number of decimal places I see is 2, which makes our LCD 100. And that's what we multiply everything by, not just the decimal terms, everything by. So we take the 100 times the 0.05x plus the, and I'll write that in a minute, plus the 100 times the 20 equals to the 100 times the 0.10x plus the 5, the 100 times the 5. Got a little squishy there, but you can read it, hopefully. 100 times the 0.05x plus 100 times the 20. The 20 didn't have a decimal. Don't do that. Wrong. Every single term gets the LCD multiplier. 100 times the 0.10x. That got a little ugly. I can make that better. That's fine. 10x. There we go. Plus 100 times the 5. All right, what happens when you multiply by 100? Each of these decimals just moves right twice. So this one goes right twice and it becomes a 5x. No more decimal. 100 times 20 is going to be 2,000. 100 times 0.1x, move the decimal right twice and you get 10x. 100 times 5 is, well, 500. No more decimals, much easier on la cabeza. That means head. Much easier on the brain, much easier on the eyes. Now we're just going to move things from side to side. Doesn't matter which way you move the x's. I prefer to move the smaller x. So I'm going to subtract 5x on both sides. If you subtract 10x on both sides, that's fine. Your next step is just going to look slightly different. Now the x's are going right, which means the constants move left. So I need to subtract 500 on both sides to be efficient. If you subtracted 10x, that means here you'd be subtracting 2,000. If you want to split this into 2 steps, be my guest, nobody cares. The x's on the left cancel. 2,000 minus 500 is 1,500. And that's going to give us an equals. 10 minus 5 is 5, so that's 5x. The 500s cancel. Last step, divide both sides by 5. 5 goes into 15 3 times. Tag the zeros along. And you get that x is equal to 300. Now remember, with word problems, you have to check your answer, make sure that it actually makes sense in a real world context, and label things. There could be multiple answers like we saw in example 1. Well, they said, at how many texts does your plan choice not matter? What is x? X is the number of texts. See, I know what x is because I labeled it. If I hadn't labeled it, I might be confused at this point, because sometimes x is not the answer. So it's 300 texts. When you send 300 texts, that means it doesn't matter whether you chose plan A or plan B, your cost will be the same. Feel free to plug it into one of those costs or both of those costs to see what it would be. Plan B is a little easier. 300 times 10 cents is just going to be 30. 30 plus 5 is 35. So $35. If you do 300 times 0.05, that's going to be 15. 15 plus 20 is $35. This is what's known as a break-even point. It means that if you send less than 300 texts, one of the plans is better. And it means if you send more than 300 texts, the other plan is better. And you can infer that either logically by the lower fixed cost. So I would go with the plan B for the $5 fixed cost if I'm going to go less than 300 texts, or you could plug in some numbers and figure it out on your own. If I was going to send 400 or 500 or 600 texts, I'd go with plan A. I would take the higher fixed cost because the lower variable cost would catch up and save us money in the long term. You can also graph these. These would look like lines. And at whatever number of texts you're sending, the lower line would be the cheaper plan. We'll talk about that another day. All right, so that's a pretty good problem. Let's just erase this stuff. It's all the same. Cool. All right, next example, example 3. Your local computer store is having a terrific sale on digital cameras. After a words are hard. After a 40% price reduction, you purchase a digital camera for $276. So this is after the price reduction. This is your final price. What was the original cost before reduction? So you found your receipt. All it says is $276. You remember that you had 40% off, but maybe you're trying to screw over the tax man and you're just going to mark this down as the original price for some refund because you take pictures for a living. And maybe the tax man comes after you for falsifying your tax documents, but whatever, we're not getting into all that. But you're trying to go, oh, well, what was the original price at the store if I want to be slick? Or maybe there's another reason you're doing that. Who knows? Who cares? So what do we know? What do we not know? Well, we know the final price. We know the final price of $276. We don't know the original price, sticker price. Now, that's probably going to get called X because of that. What else do we know? We know there's a 40% price reduction. So this is also a known reduction. So if you're familiar with how tax works at the store, you take your original sticker price, you add your tax price, and that gives you your total price. Sale prices work similarly, but instead of like adding a tax, you subtract a discount. So you take your sticker price, you subtract your discount price, and that's going to give you your final sale price. So here's the knowns and unknowns just labeled a little cleaner. A 40% reduction. So that's going to be part of the discount. It's not the discount in dollars, it's the discount as a percent. Be careful there, we're going to have more work to do. We know the final sale price of $276, and we know we're going to call the original cost X, or N, or whatever letter you like. C, P, who cares? I like X. So again, your sale price or your final price would be the original price minus the discount. Oops, don't show that yet. So your final price is the difference of the original price and a dollar amount of discount. So this is a dollar amount minus a dollar amount. The discount is not 40%. That's the discount rate. What's the discount? It's 40% of the original price. So what's interesting is the discount also involves the original price. And if you remember word associations, the word of means times. So 40% of the original price would be 40% times the original price. So this equation is actually going to have something else to stuff into it because the discount is once again the discount rate times the original price. So reduction, discount rate, those are the same things. So what that means is we can take this thing right here, final sale price we leave alone, original price we leave alone, but let's write the discount as something we can use a little more cleanly, which was the reduction rate times the original price. So again, all I'm doing is changing this into this. It sounds way worse than it actually is. Now, some of you might know, well, hold on. If you're originally paying 100% for an item and you've got 60% off, I'm sorry, 40% off, spoilers, that means you're just paying 60% of the item. So you could say the final price is what we call the complement times the original price. You understand that? Go for it, but that's not the way I teach things in here, even though I technically did just teach it. All right, so let's start plugging in things that we know. Do we know the final sale price? Yes, it's $276. So the left side's going to be a $276. Do we know the original price? No, so we call that an X. Minus, do we know the reduction? Yes, 40%. Do we know the original price? Once again, no, we call it X. So this becomes the final sale price of $276 equals the original price of X minus, now I'm going to write this in red because this is not going to be good, 40% times the original price, which the original price is X. See, I wrote the X in black, but the 40% is in red. Why can I not do this? Because you can't put percents in equations. You can't put percents in equations. You can't put percents in equations. So a little side note, you have to change the 40% to its decimal equivalent. Its decimal moves left twice, and it's going to be 0.40 or 0.4, whichever you prefer. I'm actually going to go with the 0.4 this time, since we're not talking dollars and cents explicitly. So let's erase where I had 40% and put its decimal equivalent of 0.4. If you want the dot there, that's fine. It's up to you. Now, there are two ways you can continue from here. You can say, oh, well, this is a 1. 1 minus 0.4 is 0.6. I have a feeling a lot of you are not going to realize that's a 1 and you can do 1 minus 0.4, or you're going to forget how you do decimal subtraction, which terrifies me, and you're going to scream for a calculator, which no, you're not allowed in here yet, not for this stuff. This is supposed to be knowledge you have. Go practice if you don't have it. But what you can also do is say, oh, there's decimals here. We just did an equation with decimals. What do? Find an LCD and clear it. That's perfectly fine. So we can say our LCD. There's no decimals on the 276. There's none on the X. There's 1 on the 0.4. So our LCD is 10. So we take 10 times everything. Ten times 276 is 2760. That would then be 10x minus 10 times 0.4 is 4x. 10x minus 4x is 6x. You then have to divide both sides by 6 to finish this. Not even a lot of stuff happening here. Oh boy, 4-digit division. Well, maybe you want to go to the side and show that work. No calculators. 6 will go into 2, none. So don't write anything over the 2. 6 will go into 27 4 times. 4 times 6 is 24. Subtract, you get 3, bring down the 6. 6 will go into 36 6 times perfectly. Subtract, you get 0. You bring down the 0, it goes in 0, etc., etc., etc. It's 460. So x is equal to 460. What is x? This is something you should always ask yourself with these word problems. What is x? Well, we said x was the original cost. What was the point of this problem? To find the original cost. So did we just solve it? Yes, but we should label things better. The original cost, or the sticker price, would be 460. Well, writing this by hand, you better put your units. It's generally not an issue in my math lab. Does it make sense? Something else I said you should do to check your answers? Well, I hope it makes sense. It's more than the sale price. If you came up with an original cost of $100 and you paid $276 after a discount, sounds like you got screwed over at the store. Maybe you messed up some decimal division somewhere, multiplication, and you got an original cost of $4,600. I don't think you just got 40% off if the original price was $4,600 and you only paid $276. That sounds like a 95% sale price. That sounds like a fire sale going out of business. Also, most cameras don't cost $4,600. Sure, they do exist. There are definitely lenses that cost that much. So again, make sense of your answers. If you did not multiply everything by the 10 here, what you would have done, you would have had the 1 minus the 0.4, which would end up being 0.6. You would have to divide both sides by 0.6. You'd have to remember that to divide by decimals, You move the decimal right until it's whole, but you do the same thing at top. You'd end up doing 2,760 divided by 6, the exact same division, giving you the exact same answer. And again, technically, that's a skill you're supposed to have at this level, but we have ways of avoiding it. All right, let's do another. And yeah, that's fine. Example 4, investing, one of my favorite topics. Bob invests $50,000 into 2 accounts earning simple interest. Not typical, but go with it. When you're investing, you tend to invest in things that have variable rates, like the stock market. But if you're just putting your money into savings accounts and CDs, that's fine. You're not going to get 7 and 15% in these accounts. These are very unrealistic numbers. If you know how to get a 15% fixed rate on something, please talk to me after class. Let's make some money together. After a year, Bob has earned $6,000 in interest between these 2 accounts. So he split his money into 2 accounts. Maybe that 15% account has got some risk, and maybe that bank's going to close and he'd lose all his money if they close. I don't know. Otherwise, I just put all of it in the 15% if I know I'm going to get 15%. But again, not the point of the problem. So the interest he earned from the 7% account and the interest he earned from the 15% account would add up to $6,000. I'm not saying he earned $6,000 from one or $6,000 from the other. I'm saying he earned $6,000 in total. If the 2 accounts he invested in earned 7% and 15% simple interest per year, which means they only accrue interest once over the year, how much did he invest in each? So we're not doing compound interest in here. That's something I'd love to talk about, but we do very, 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 very briefly in chapter 4. How much did he invest in each? So as a reminder, your simple interest formula, which hopefully everyone remembers, PERT, terrible shampoo, but a good formula. Principal times rate times time is how we get simple interest. Hold on one second, sorry. All right. So simple interest is the triple product of principal, interest, and time. Got to have that memorized. That's how we're going to calculate the interest for account A. That's how we're going to calculate the interest for account B. So what's the principal? We don't know how much we put in each of these accounts. So you might say, we'll call them both X. You can't do that, though. You might say, oh, it's $50,000. No, we didn't put $50,000 in both. We split our $50,000 into both. So that means if I put $10,000 into account A, I'd have to put $40,000 into account B. If I put $20,000 in account A, it means I'd have to put $30,000 in account B. If I put $5 in account A, that means I'd put $49,995 in account B. These are important things to talk about because you can say one of them, you can call one of these accounts principals X, but you're going to have to call the other one a relationship between the 50,000 and the X. So if I put 10,000 in the first account, I know I put 40 in the other. And that's because 50 minus 10 is 40. So I took the total minus what I put in the first. If I put 20 in the first account, I put 30 in the second because 50 minus 20 is 30. The total minus the first is the second. That actually gives us the equation when you think about it. You take whatever you put in the first, you subtract it from 50 grand. As I said, from, that means reverse the order, and that gives you what you put in the second. Oops. So let's call, hold on, let me do this so you can't see my screen. Come on. I just have my equation a line higher. So let's call the amount we put in the 15% X. Why? Because that's just what I happen to choose. I could have called the amount in the 7% X and it just would have flip-flopped everything. But in the end, you'd get the same answers. So I'm going to say we put X dollars in the 15% account. Now I said, how do you find out what you put in the other? It's the total minus the first, the total being the 50,000, the first being X. We don't know what it was X. So how much did we invest in the 7% account? The total of 50 grand minus what we put in the first. All right, so that's the principles. What are the rates? Well, the rates are clearly on screen, 15% and 7%, but make sure that you convert them to decimals. So 15% is going to end up being 0.15. 7% will end up being 0.07. 0.7, that would be 70%. That'd be amazing. Find me a 70% account and let's go make some money. How about the time? Well, the time, how much did he invest in, I'm sorry, how much interest did he get? $6,000 between these two accounts in 1 year, after a year. So T is equal to 1 year. So now we can say that the interest from the 15% account plus the interest from the 7% account is equal to $6,000. This is the equation we're using our words. Where did this come from? This comes from right here. He earned $6,000 in interest between the two accounts. So you take the interest from account A, you add the interest from account B, and you get 6 grand. You get the total interest. So that's our equation using words. We have our knowns and unknowns up here. We have our equation using our words. So now let's fill in the equation with our numbers and variables. What's the interest from the 15% account? It's its principal times its rate times its time. Now with a time of 1, we don't really need to write the .1. We can. It's really just the principal times the rate, where the principal is X and the rate is 15%, 0.15. How much interest from the 7% account? Well, that's the principal of 50 grand minus X times its rate of 0.07. So interest from the 50% account, principal of X, I want black, times its rate, which was 0.15, and I'll write the time, which is 1, just for completion's sake. Then plus the interest from the 7% account, I'm going to do in blue, so this one will be in blue. That's the principal, which is this 50,000 minus X. Now, if I do this times the 7%, this is not good enough because it only looks like we're multiplying the X and the 0.07. So this is kind of interesting, pun intended, because that's a binomial, you have to wrap it in parentheses. And then times its time, which was 1 year. And then we say equal to the total interest of $6,000. And then we're just going to clean this up and solve it. 0.15 times 1 is 0.15. Just put that in front of the X. We don't really need to see the times. Sorry, we don't really need to see the times 1. And I like to have the 0.07 in front. Maybe you skip rewriting it. It's up to you. So I didn't really do too much here. Now you might say, well, let me go ahead and multiply everything by 100 because that LCD would be, there's 2 decimals at most, so LCD of 100. You can, but a lot of people will end up multiplying it in the parentheses too, so I think that's a bad idea. I actually prefer that you go ahead and distribute. That's 0.15x plus 7 times 5 is 35. You got 2 decimals here, 1, 2, 3, 4 zeros here, which means we're just going to trim out 2 of those zeros. Feel free to show your decimal multiplication if that didn't make any sense to you. So 3,500, then minus 0.07x equals 6,000. Show it longhand if you have to, right? 50,000 on top and 0.07 on bottom. Same as I've already said, there's 2 decimals, no decimals, 2 decimals, no decimals. So your LCD is 100. And that's what we're going to multiply every single term by to make this easier. So 100 times the 0.15x plus 100 times the 3500 minus 100 times the 0.07x equals 100 times the 6,000. We're just going to move each decimal right twice. So that becomes 15x plus 4 zeros, 350,000 minus 7x equals 1, 2, 3, 4, 5, 600,000. And then no more decimals. Decimals go bye-bye. 15x minus 7x is going to be 8x. Give myself some room here. So 8x. Wrong color. Why did I change colors? 8x plus 350,000 equals 600,000. Subtract the 350,000 on both sides. We'll get 8x is equal to 250,000. Divide both sides by 8. If you need to show the long division, you can. Eight can't go into 2, but it can go into 25 3 times. 3 times 8 is 24. Subtract and you get a 1. Bring down your 0. 8 will go into 10 once. 1 times 8 is 8. Subtract and you get a 2. Bring down the next 0. 8 will go into 20 twice. 2 times 8 is 16. Subtract and you get 4. Bring down the next 0. 8 will go into 45 times perfectly. So that subtraction will be 0, which just means you have that next 0 up there. Giving us an answer of x equals 31250. What is x? X was one of the principles, but labeling them correctly is important. You can't just roll the dice and say, oh, it was the 7%, oh, it was the 15%. This is why labeling things well is helpful and awesome. So we said we called the principal at 15% x, which makes the other one 50 grand minus that. So for our answer, the principal at 15% would be $31,250. And then the principal at 7% would be 50,000 minus that. That's a 50K minus 31,250. And when you show that subtraction, you'll end up with, what's that, $18,750. And let me tell you, if you get those numbers right, but put them in the wrong boxes in my math lab, you're going to be kicking yourself for goofing that up, especially if it's a test. Again, if you say, hey, Mr. Beckner, I showed good work, go check out question 17, and I see that your answers are just flip-flopped, you'll get most of your credit, maybe even all if it was labeled correctly on your paper. But at worst, I'd take 1 point from it. This is definitely the most involved problem of the bunch. Let's review it. We knew how much we invested. We knew how much we got in interest between 2 accounts. We knew what the interest rates were, but we didn't know how much we invested in each. We had to remember our simple interest formula, principal times rate times time, where the t was a 1. we had to understand how to label the principles, and this is where people goof the most. A lot of people will do x minus 50,000 instead of 50,000 minus x for one of them. Some people will just call them x and y and not know where to go from there. Some people will just say it's 25 each, and then, oh, that we're done. These are not true statements, though. You need to call one of them x, and then the other the total minus the first, the 50,000 minus the x. This is imperative. There are a lot of problems that can end up working out like this. I might say that you ran across 2 paths and your total mileage was 11 miles, and I tell you something small about them, but you can't say, oh, well, I know it was 2 and 9 or 3 and 8 or something. You have to say the first one's x and the second one would be 11 minus x if I told you nothing about them. We know that we add the interest to get the total interest, and then we just plug everything that we know and don't know into that. And then we use our decimal solving skills or equation solving skills and decimals and LCDs and all that jazz to get an x. We ask ourselves, what is x? We label the one answer we know now. We find the other one based on that simple equation, and we label everything appropriately. All right. You see a lot of the same stuff here. So that's the last word problem we'll do for the day, but we're not done with this section. We're going to do some stuff with formulas. Mr. Beckner, we were just doing stuff with formulas. We were just doing word problems with formulas. Well, these are different formulas. These are formulas where we're not going to be plugging numbers into them. So like taking the formula for the perimeter of a rectangle, P equals 2L plus 2W, and just solving it for one of the variables. There are times when doing this is important. Maybe you work a job where you know 10,000 different perimeters you want and 10,000 different widths you want and want to know what the respective lengths would have to be. So it would be very much a pain in the butt for you to have P equals 2L plus 2W, plug those 10,000 parameters in, solve 10,000 equations, and get the answer 10,000 times. What would be much easier is to rearrange the equation to go ahead and be solved for your length or width or whatever you didn't know was. Put that equation in Excel one time, put your 10,000 parameters in Excel, apply the formula to all 10,000 cells and go home in about 5 minutes. Versus having to solve the equation 10,000 times is going to take you a week. I'd rather be done in 5 minutes. So it's efficiency. So how do we solve an equation for a variable if there's more than one variable? You just treat everything else as if it were a constant. Now, I don't mean that you're going to start saying L plus Q is 7 and rewrite that as a 7 or something like that. I mean, you just move them from side to side like they were numbers. You can divide them like they're numbers. But it ends up being what I call a hipster problem. It looks more complicated than it actually is because you won't really do any work. So you handle any variable not being solved for as if it were a number, as if it were a constant. When there's more than one of the variables being solved for, you will likely need to move it to the same side and factor it out as a GCF. We won't see this at first, but we will see one by the end. All right. Sorry, I was trying to move something. So example, what are we up to? 5. Solve for the indicated variable A. Well, I was just talking about this, so let's go with it. P equals 2L plus 2W. We're going to solve this for L. Here's what I like to do. I like to circle the variable I'm supposed to solve for. That's my flag that says, hey, look at me, get me by myself. I need to be quarantined. L's coughing and hacking. So the 2 next to it needs to get away from it. The 2W after it needs to get away from it. Think about this in the same way you would if these were just numbers. If this was, say, 2L plus 25, you'd subtract 25 on both sides and then divide by 2. But you're not going to subtract by 25. You're going to subtract 2W on both sides. I don't just subtract the 2. I don't just subtract the W. I have to subtract those pieces together because it's one term. Now, what happens here? Well, the 2W's cancel on the right side. So you get 2L on the right side. That's all that's left over for now. And on the left side, P minus 2W is clearly 17, right? This is 17. No, it's not 17. What are you on, Mr. Beckner? P minus 2W, I have no idea how that simplifies. Well, guess what? No one does. You leave it alone. That's what I meant by it's a hipster problem. It looks more complicated than it actually is. You don't have any arithmetic to do because you can't do it. You're just stuck with that. Now, normally this might be something like 17 equals 2L. You would divide both sides by 2, and 17 over 2 would be your answer. Well, guess what? You're still trying to solve for this L. So how do we do that? We divide both sides by the number with it. Divide both sides by 2. Now, I prefer doing this as an all-at-once division. I'm going to show you an alternative way to write it, though, after. So P minus 2W over 2. Now, a lot of people will do this. They'll cancel these 2's. Oh, 2 in the top, 2 in the bottom. No, you can't cancel on the left-hand side. These do not reduce because you need a 2 everywhere to reduce. That says no reduction. It's P minus 2W all over 2 equals, but this is just a single fraction, so the 2's do cancel. And this would be our answer. And that's a perfectly fine answer. If you don't like doing it that way, you can do what's known as a split division. You can divide, term by term by 2. I do not care which technique you do for now. However, when we get to lines, when we get to graphing lines, things like 2x plus 3y equals 6, I actually prefer this later. This is better later. The P over 2, nothing happens. Minus the 2W over 2. Now this one, you can cancel the 2's because there's no pluses or minuses separating terms in a fraction. This one, same thing, you can cancel the 2's, so you get this. And you might say, well, Mr. Beckner, clearly the second answer is simpler because you were able to reduce more. Yeah, arguably. But there are times when this is actually a better format for something like literal equations. So these are both acceptable answers, and before anyone asks, yes, my math lab will count both as correct. You will not get either of them wrong on a test. Asterisks. Let's say we had 2p minus 4w over 2 equals 2l over 2. This is a different problem. Let's just say this is what we had. This was a 4 here, and this was a 2 here. This one you could actually reduce because there's a 2 as a factor everywhere. You can reduce here, but you have to take it from everything. You take a 2 from here and it makes it a 1. You take a 2 from here and it makes it a 2. Take a 2 from here and it makes it a 1. So what you get would be P minus 2W over 1 equals L, which is just P minus 2W equals L. That will be an issue moving forward if you don't split your fractions. You can only cancel these fractions that have pluses and minuses separating terms if that common factor is everywhere. It's a very easy mistake to make, and I know some of you are going to make it. It's just how things work. I would love it if everyone learns and doesn't. Practice, and maybe you will. All right, let's do another. B. A equals B plus C, D, E. And let's solve this for D. So again, what I like to do is circle the variable being solved for. It says, hey, look at me, isolate me, quarantine me, get me by myself. Cough, hack, I can't smell anything, whatever. So this B sitting by itself, adding to it needs to move. And then the C and the E multiplying by it need to move. Now think back to your equations. What do we like to move first? Additions and subtractions or multiplications and divisions? We like to move the additions. So the first thing you should do is subtract B on both sides. A minus B is 49, right? No, it's A minus B. I can't do anything with it. These B's cancel on the right-hand side, though, and we get C, D, E. Now, once again, I'm solving for D. So everything that's not D needs to go away from it. Well, the cool thing is, since these are both multiplications, you can actually knock this out all at once. You could divide by C and then E. That's a terrible looking C. It looks like an E. Or you can do it all at once. And I like to do the division this way for formulas. So that's A minus B divided by CE is equal to D. Once again, I have no idea what A minus B over CE is. So you leave it alone. Question C, A equals P plus PRT is actually how you find future value for simple interest. You take what you had and add your interest. So you had 50 grand, you had 6 grand, now you got 56 grand. P is what you had, PRT is interest, what you gained, A is future value. And we want to solve this for P. Now, this one's different. You got P more than once. So if you had like X plus 3x, it would be 4x. If you had 7x plus 3x, it would be 10x. Well, this is P plus PRT, and I don't know what 1 plus RT is. So combining like terms is kind of wacky here. This is that note I mentioned previously. When there is more than one of these variables being solved for, you will likely have to move it to the same side, which is already the case here. They're already on the same side, and factor it out as a GCF. So we have a GCF of P. So we take that P out, we open a parentheses. And then we divide each term by the GCF. So we're taking the P away from it. Now this term had a P, we're taking it away, so we're left with nothing, question mark? Well, not really, because we're dividing. If you leave this blank, you're implying it's a 0 when it's really a 1. P divided by P is 1. See, if you redistribute it, it makes sense. And then when you take the P away from PRT, you're just left with R and T. If you're rusty with factoring out GCFs, as always, practice on your own time. We'll get into some light factoring in here, light practice, but it's going to go quick. Now, what are we solving for? We're solving for this P here. This is just P times something, because it's a parentheses, P times something. If it was P times 5, we would divide both sides by 5. So guess what? We divide both sides by what the parentheses is. We divide by parentheses 1 plus RT. Doesn't matter how simple or ugly it is. It's just a division, just one step. And it actually gives us the answer. A divided by 1 plus RT. 22. No. And I really don't even need that parenthesis. The cool thing is those cancel, just leaving us with our p. Because anything divided by itself is 1. So if you don't want to write the parentheses, it looks like this. Now notice, I'm not going to say notice, note that you can't split up the denominator here. You can't say a over 1 plus a over RT. It only works for tops, not bottoms. You cannot say this is a over 1 plus a over RT. It don't work that way. Let's do one that's similar to C, but step it up a notch. Let's practice that GCF stuff again. A plus D equals DE minus B. And we're going to solve this for D. Uh-oh. We got a D here, and we got a D here. There's 2 of them. And uh-oh, they're not on the same side. So those steps earlier said that we should move the D's all to one side, move everything that doesn't have a D to the other side, and then we'll do this factoring thing. It doesn't matter which way you move your D's. I'm going to move them right because that's my choice. I choose to move the D on the left to the right. And I'm going to put it under the DE, but very similar to what we've seen over and over and over so far is that they're not going to be like terms. Now, if I move the D's right, if I move everything that has a D to the right, everything that doesn't have a D needs to go left. This B does not have a D, so I move it left. A plus B is A plus B. The D's cancel, equals. DE minus D is not E. That's like saying 5x minus x is 5. It would actually be 4x, but these aren't like terms. They're not combinable. DE minus D is DE minus D. These B's will cancel. Then we can say here, because we have a D here, and we have a D here, there's still 2 of them, which means we need to do that GCF thing again. And the GCF is the common letter of D. They both have it, so we can take it from them. We will leave the left-hand side alone. A plus B equals. We will take out the GCF of D. We open a parentheses, and then inside goes what's left over after we divide. DE, when you divide out a D, when you take it from it, you're left with E, then a minus. This D, when you take it away, is not blank. It's not 0. It's 1 because we're dividing. Finally, remember, what are we solving for? We're solving for D. That's D times something. So we divide by the something. We divide both sides by E minus 1. Giving us A plus B over E minus 1 equals D. And if you write it with the parentheses in the bottom, that's fine too. I'm going to skip the double writing though. So we just finished 1.3, which means we can say the homework is due in a week. So that'll be the 27th. The 1.2 due date should have already been in my math lab. I will update the 1.3 due date later today to reflect that. We will definitely not finish 1.4 today, but we will start it. Complex numbers. I've heard so many students whine and complain about complex numbers because they involve imaginary numbers. Mr. Beckner, why are we dealing with things that don't exist? Actually, they do exist. It's a terrible name. It's a very poor name. It's named for a very important reason, and it has to deal with their x-intercepts. If you graph them, it's that those are imaginary, those don't exist. But imaginary numbers are actually a very, very, very important part of our world. Engineering and science, this stuff is littered all over the place. And unfortunately, the concepts are a bit out of our pay grade to talk about in here. But just trust me, there are tons of things that involve imaginary numbers, like people building bridges so that the wind doesn't knock them over. Imaginary numbers are involved. That's just one example. So what is an imaginary number? What is a complex number? Imaginary numbers are involved with something that for the longest time we said we're not allowed to do. When you take a square root of 4, it's 2. You take a square root of 9, it's 3. When you take a square root of 8, you simplify it to 2 square root of 2. You can't take a square root of 5 and have it be a whole number, but you can take it. It's 2.23 something, blah, 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 blah. But what we have always said up to this point is you asterisks can't take the square root of a negative because there's no real number that when you multiply it by itself makes a negative. So like the square root of -4 before we would have said is not real. Since 2 times 2 is 4 and -2 times -2 is +4 as well. You can't take 2 times -2 because those aren't the same number. That's the point of a square root. They have to be the same number. So we call it imaginary. Because these square roots of negatives play such an important role in our universe, we can't just brush it under the rug and forget about it. We have to deal with it implicitly. So one mathematician one day decided, hey, let's just call the base square root of a negative I for imaginary. So they invented it, they created it, and we're going to invent it and create it right now. So we say, whenever we see the square root of a -1, from now on, we call it I. And this is our base imaginary number. This is a definition. We are saying from now on, whenever we have a square root of -1, call it I. And this will enable us to say the square root of -4 is something. The square root of -9 is something. The square root of -8 is something, instead of just throwing it in the trash. Some teachers might tell you it doesn't exist, but it's more appropriately told to be not real. So with this in mind, any complex number, which is a combo of real and imaginary numbers, can be written as, and I'm actually going to write this out with my pen because it's the important part, A plus B I, where A is the real part because there's no I with it, B is the imaginary part because there is an I with it. This is actually a very, very bold statement. Any number in the entire world can be written as the sum of a real part and an imaginary part. What it means is you can't have i's in denominators of something. What it means is you can't have I squareds in there. What it means is you can't have square roots of i's in there. There's a lot of implicit statements with this, some of which we'll deal with, some of which are above our pay grade. One in particular, let's go ahead and talk about. So I said, no, you can't have an I squared. You can't have an I cubed. You can't have an I to the fourth and an answer. It's not simplified. And let's focus on the most important of those. If we can't have I squared, in an answer, what is it? So I squared is equal to what? Well, I is the square root of -1. Let's use the fact that I is the square root of -1. Let's go backwards. So that I is the square root of -1, but then we still have the square here. So what I rewrote was this part. I wrote the I as square root of -1, and I still have the square there. Well, guess what squares and square roots do? Squares and square roots cancel, so this is equal to -1. So I squared is actually equal to -1. This you will use over and 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 over. You can do this to find out what I cubed is, what I to the fourth is, what I to the fifth is, what I to the sixth, seventh, eighth, and millionth is. The cool thing is it's actually known as a cyclical group. It's the same 4 answers over and over and over. In particular, I cubed is I to the fourth is +1. Then I to the fifth is going to be I to the sixth is I squared, which is -1. I to the seventh is the same as I cubed, which is I to the eighth is the same as I to the fourth, which is 1. So you just keep getting the same pattern of I, -1, I, 1 over and over and over. We're not going to use that fact in this course, but you could see that in a later math class. The only ones we'll see are I and I squared in here. So every time you have an I squared, you better write that as a -1 or your answer is not complete. There could be a little bit more work to do. There could be a lot more work to do. Example 1, simplify. So for the square root of -4, what we saw at the very beginning, we will no longer say it doesn't exist because that was wrong. We will no longer say it's not real. We will simplify this. Now, if you want to take the extra steps to break this down as a product, be my guest, that's up to you. Because we defined what the square root of -1 is, it's I. So let's try and break this into a number times a negative. So how about the square root of 4 times -1? And then we know square roots of products are products of square roots, so we can write this as the square root of 4 times the square root of -1. We know the square root of 4 is 2. And we know that from now on, whenever we have a square root of a -1, we call it I. So we get 2I as our answer. And if you don't believe me, take 2I times 2I. The 2 times 2 is 4. I times I is I squared, which is -1. You get -4. It works. The shortcut here, a lot of people just say square root of -4 because of the negative. You pull out an I, the square root of 4 is 2, and then you're done. Whenever you have a square root of a negative, you pull out an I. It sounds gross. Whenever you have the square root of a negative, you pull out an I. Do I care if you take the shortcut? Be my guest. How about the square root of -50? Step it up a little. So you can write this as a square root of a product. You can go ahead and split up the 50 and the negative. We'll take this the long way. You can write the negative first or second, nobody cares. So you have the square root of 50 times the square root of -1, which would be the square root of 50 times I. But here's the thing, this square root of 50 can be simplified. This isn't good enough. Whenever you have a number that you can't take a square root of, but you can write it as a product of two numbers where one of them you can take the square root of, you have to split this up. So this is something that you might need to de-rust on from, I think, P3. I think that's where the radicals were. So you might say, all right, what are all the different ways we can write 50 as a product? 1 times 50, which is useless, 2 times 25, or 5 times 10. Out of those options, think about which one you know a square root of. Well, I know the square root of 25, so let's do it that way. So let's do the square root of 25 times 2, and then times the I. Now that I is not under the square root. Please be very careful there. It's very important. Well, I can break up that as a product, the square root of 25 times the square root of 2 times I. We know the square root of 25 is 5. We do not know the square root of 2, so leave it alone. And we know that I is still an I. This, in my opinion, is a bad format for an answer. And you want to know why? Because a lot of people will do this. They'll just keep extending their square root and put the I under it. You can't have square roots of i's. That's terrible. So your better way to write this is actually 5, then the I, then the square root of 2. This is the best way to answer this. That way you know that I won't accidentally end up under the square root of 2. Is this still correct over here, the bad format? Yes. Will you still get full credit for it? Yes, as long as you make sure the I isn't under the square root of 2. You will never have I's under square roots and answers. You should never see them in the pre-calc class. That's horrible. It's very complicated. That's 400 level math stuff. How about a cube root of negative 27, and we will stop after this example. So a lot of people will break it up this way. They'll say cube root of 27 times cube root of negative 1. And they'll say the cube root of 27 is 3, and the cube root of a negative 1 is I. So a lot of people will say, oh, this is 3i. Notice I pulled out the red because nope, it's not 3i. This is not 3i. This is not 3i. You know why this isn't 3i? Because your base imaginary number said nothing about cube roots. This is square roots only. This is square roots only. Did we have a problem taking a cube root of a negative before? No, we didn't. Because a negative times a negative times a negative is a negative. This was never a problem. So 3 times 3 times 3 is 27. Negative 3 times negative 3 times negative 3 is negative 27. Your i's are only involved with square roots. Not cube roots, not fifth roots, not seventh roots, not ninth roots. What about fourth roots, sixth roots, and eighth roots, etc.? Well, actually, you're still just going to say not real. We're not going to say they're anything having to do with I. I's are only square roots. Let's just leave that under the rug for now and save it for a 400 level math class. Because that would be the square root of an I, which again just gets a little crazy, a little above our pay grade. So watch out for this. This is a nice trick that can be thrown on a homework problem or a test problem just to make sure you're staying on your toes. I will never ask you what the fourth root, sixth root, or eighth root of a number is. I'll only ask you square roots or odd roots of negative numbers, that is. All right. So again, remember that 1.2 homework is going to be due on the 25th. 1.3 homework is going to be due on the 27th. Stay warm, stay safe. Hopefully nobody loses any power. Hopefully we don't get too much snow. If you like the snow, enjoy it. If you don't like it, deal with it. I'm definitely in one of those boats. I'd rather not have to shovel my wide driveway, but it is what it is. Email me if you have any questions. Stay on top of your My Math Lab homework. Do that Chapter P homework because that'll get you your 5 bonus points and be good practice for yourself as well. Go to Purple Math or Khan Academy if you need more help with stuff like square roots of 50 and exponent rules and all that jazz. I'm still waiting to hear the hours for the tutoring center, but if you just Google TCC Tutoring Center, you can find the links to the request forms up there as well. But I will send it out over email when I have it. Besides that, have a good weekend, stay safe, and we'll see you next time. Take care, everybody.